So if you look at the formal definition of PCA, it says that the variance of projection points in the direction Z1 is going to be maximum, and the sum of square of perpendicular distance of these points are going to be minimum. I will suggest you to pause this video, take a look. Do you understand it? If not, don't worry. The promise is that in next probably 10 minutes you will understand every word of it what is written here. So now let's start the journey. So let's first understand what is the variance in the data through some visual examples in 2D case. So take a look at this data. In this data, if I ask you which dimension data appears to have more variance, in X dimension, in Y dimension, what are you going to say? You can pause and you can think of. Now if you think of, if you take a look, it's varying much more in X-axis. In X-axis, it's changing from 0.75 probably to 1.75. Whereas in Y-axis, if you take a look, it's just between 0.4 to 0.6. So what did you do? In fact, like you probably draw perpendicular here, and wherever it is cutting, you saw how much it is varying here. And you found it's varying much more here than here. But if I ask you intuitively why this question is being asked, which dimension is varying more? Now if you take a look, and think of for example, it's like a grade. So in grade, if suppose you have 3 papers, in 2 papers everybody is getting almost similar marks, then and there is one paper where there is huge difference between among different students, then that particular paper will decide who has got the maximum, who has got the least, because in other 2 paper almost everybody has got similar marks. Similarly for movie, like on some parameters, probably action, probably cinematography, probably every movie will be almost similar. There will be some parameters which have huge variance, and that's what will decide the success of movie. So the dimension which is varying more will help you understand the final impact. And that's why you like to understand which dimension is varying more. Now if you think of what did you do, you draw perpendicular lines to x-axis from all the points, and where it is cutting, these are the projection points. Then you found the variance of these projection points, and you said that data is varying much more in the x-axis. Similarly, you can draw perpendicular on y-axis, and then where it is cutting y-axis, those are projection point on y-axis, and the variance of projection points gives you the variance of this data in the dimension of y-axis. If you think of grid line, actually it's very much what you are trying to draw perpendicular. Without even drawing perpendicular, it is varying from 0.8 to 1.8, and this data is probably 0.4 to somewhere here. So grid line eliminates the need of making multiple projection, and by just taking a look at the point and the grid line, how much it is varying. So lots of variance in x dimension and much less variance in y dimension. If I ask you this data, here which dimension is varying more? Obviously y-axis. See, in x-axis it's just 0.4 to 0.6, in y-axis it is varying a lot. Now if I ask you which dimension it is varying more, what is going to be your answer? If you take a look, it has varied a lot in this dimension as well as it has varied a lot in this dimension. These two are not in the same scale, but still you can say this data is varying a lot in both dimensions. Now if I ask you, and you can pause the video and think of this question, can you find another dimension, another direction where variance is much more than x direction, x dimension, y dimension? Think of, you can actually make a line like this, red dashed line, and if you put projections from all the points on this red lines, you will find that the projection points is varying much more, and this time it's varying much more than x dimension and y dimension. Similarly, you can make a blue dotted line which is perpendicular to this red dashed line, and again from all data points you can put projection on these blue dotted line, and you can see how much the projection points are varying in this dimension. And obviously you can see that in blue dotted dimension the variance is much less than the variance in the red dashed line. So the variance is much more in the direction of red dashed line than blue dotted line. So if you think of what did you do, you found the direction where the data has maximum variance. This direction is called the first principal component, and the variance in this direction is called the variance of first principal component or the first eigenvalue. Now by very nature, if you think of in the data, you found the direction which has the maximum dimension, maximum variance. So it has to happen that the first eigenvalue has to be the big one. Now what did you do in the second? You found the direction which has the residual variance, and this you call the second principal component. In our case it is the blue dotted line, because if you think of this data, it has got maximum variance. If you draw perpendicular from all the points on these on this red dashed line, you will find it's varying much more, and the perpendicular of the red dashed line has the residual variance. These two will cover the entire variance of the data because it's just a two-dimensional case. So what did you do? You found the direction which has the maximum variance, that's first principal component, and the residual variance was getting explained by the second principal component. Because by nature first principal component has the maximum variance, so first eigenvalue is the bigger one than the second eigenvalue. The blue dotted line in our case is the second principal component, and the variance of the data in this direction is called second principal component or second eigenvalue. And as explained, first eigenvalue has to be bigger than the second eigenvalue. Now it is time for me to formally introduce you to the definition of principal component analysis and its properties.